As we mentioned earlier, the real numbers are a complete ordered field, where Q is not. It is an ordered field, but it's not a complete ordered field. And the reason is, in the rational numbers, this set, the set of all rational numbers, oops, there should be a Q there. The set of all Q in the rational numbers, such that Q squared is less than 2, that has no infimum and it has no supremum. And basically that boils down to the fact that the rational numbers do not have radical 2 or negative radical 2. Now, from axioms 1 through 12 for a complete ordered field, we obtain the following properties. In other words, they could be used to prove this theorem 0.19. If these three, x, y, and z, are real numbers, then if x is less than y, then negative y is less than negative x. 0 is less than 1. If x and y are both positive, but x is between 0 and y, then when you take the reciprocals, or the multiplicative inverses, they switch order. X was less than y, but now 1 over y is less than 1 over x. Number 4, if x is less than y and z is less than 0, so a negative number, then as we know, when we multiply z by both sides, we have to reverse the inequality, which implies that yz is now less than xz. And last, number 5, x squared is greater than or equal to 0. And again, x was arbitrary, so any number, any real number squared will be at least 0. I believe most of these are proven in the text, and you can check that out on your own, but just sketching a couple of them, notice how rigorous they are. It's a very simple statement. Number 1, if x is less than y, negative y is less than negative x. Well, if x is less than y, that implies that if I add the same number to both sides, the inequality stays the same. And I'm adding negative x plus negative y to both sides. And when you do simplification, the x and negative x go to 0, you get negative y less than negative x. And number 4 is saying that if x is less than y and z is negative, then yz is less than xz. So we know by right above here that if z is less than 0, then 0 is less than negative z, and that's by part 1. Essentially, we multiplied both sides by a negative number. Then we've got negative z times x is less than negative z times y by axiom 11, because remember, negative z is actually a positive number. So the inequality doesn't change. And that together implies, using property 1 again, right above there, zy is less than zx. And that was what we wanted to prove in part 4.